Alright, so today we're going to have a look at topic 8, quadrilaterals, and we'll break topic 8 into two parts. Today we're going to have a look at part A, which include the main properties of quadrilateral basics, trapezoids, parallelograms, and rhombi. And in our next lesson, we're going to have a look at rectangles, squares, and statement if and only if. So what does this mean? And quadrilateral problems. Okay, first, basics of quadrilateral. So what is a quadrilateral? As shown here in figure 8.1, a quadrilateral ABCD usually has 4 sides, 4 vertices, and 4 angles. Actually, there are 2 types of quadrilaterals, and in this course we'll mostly focus on convex quadrilaterals, which is shown on the left side, figure 1.8, in which all interior angles of the quadrilateral are less than 180 degrees. Of course, there is another type of quadrilateral, which is a concave quadrilateral, which is shown here in figure 8.2. But in our course, we'll only focus on talking about the convex quadrilaterals, which is shown on the left. Can you follow me? Okay, and one important property of the quadrilateral is that the interior angles of any quadrilateral add to 360 degrees, including the convex or concave quadrilaterals. Can you prove this? Okay, I'll give you 3 minutes to have a look at these problems, and then we'll have a look at the solution together. Try to prove this is actually true for any quadrilateral. Alright, have you finished? Okay, Neil, can you explain your proof to the other students?
Okay. So we draw a line from like two of the opposite points, and then it splits like the quadrilateral into two triangles. And the sum of the interior angles of the triangles equal to 180. So the sum of the angles in the quadrilateral is equal to 2 times 180, which is 360.
Yeah, thank you very much. Okay, so usually when you want to prove something, you can start from what we have already known, right? So in this case, we can connect point A and C, just like Neil told us. And we already know that the sum of the interior angles of a triangle is 180 degrees, right? So let's call this angle 1, angle 2. This angle is 3, and this angle is 4 here. So we know that angle 1 plus angle 2 plus angle D equals 180 degrees. And on the other hand, if you think about triangle ABC, then we know angle 3 plus angle 4 plus angle B is also 180 degrees, right? Therefore, we know angle 1 plus angle 2 plus angle D plus angle 3 plus angle 4 plus angle B equals 360 degrees, which means angle D plus angle DCB plus angle B plus angle BAD equals 360 degrees, which means the interior angles of this quadrilateral add to 360 degrees, right? So for the other quadrilateral, you can use the same method to prove this statement is actually true, right? We can connect E and G. Then sum of these three interior angles is 180 degrees, and sum of these three interior angles is also 180 degrees. So the sum of the interior angles of this quadrilateral also adds up to 360 degrees, right? Okay, therefore you can prove this statement is actually true. So this is an important property of any quadrilateral. The interior angles of any quadrilateral add up to 360 degrees. Then we can use this property to solve some of the questions. So for example, let's consider this quick quiz. In a quadrilateral ABCD, angle ABC are known. Sorry, angle AB are known and angle C is 30 degrees more than angle D. Can you find angle D? Again, I'll give you 2 minutes to solve this question, and then we'll have a look at the solution together. Okay, of course, when you finish, you can give me your answer in the chat box, okay? Alright, since most of you have already finished, let's have a look at the solution together. So we know that the sum of the angles in quadrilateral is 360 degrees, right? Therefore, we have angle A plus angle B plus angle C plus angle D is 360 degrees. This is a property of any quadrilateral, right? And angle C is 30 more than angle D. So we know angle A is 100 degrees, angle B is 50 degrees, and angle C can be written as angle D plus 3 degrees, then plus angle D, and then you will have a equation in terms of angle D, right? Which means angle D plus 150, then plus another 30, which gives us 180 degrees. So 2 of angle D plus 180 degrees equals 360 degrees. Therefore, angle D should equal 90 degrees, right? Did you get this correctly? No problem. Okay, so this is a basic property of the quadrilateral, which is true for any quadrilateral. So next, let's have a look at some different types of quadrilaterals. First is trapezoids. Okay, first of all, the definition of trapezoid. A trapezoid is a quadrilateral that has at least one pair of parallel sides. So be careful with the keyword here, at least. So we have this diagram below is a typical diagram of a trapezoid, because in this diagram we have Wx is parallel to Zy, right? Also, the diagram on the right, as you can see here, this is a classification of different types of trapezoids. All of the trapezoids here have at least one pair of parallel sides, no matter whether the other pair of sides are parallel or not. Sometimes they are parallel. In that case, that could be a parallelogram, a rectangle, or square, or rhombus. So we'll talk about these later, okay? And sometimes the other pair of sides are not parallel. And usually when people talking about trapezoids, they're talking about cases where we have only one pair of parallel sides. But in fact, according to the definition, the rectangle, parallelogram, rhombus, and square can all be called trapezoids as well. But in this course, we'll focus on the cases where we only have one pair of parallel sides, okay? Which is shown here in this diagram. And these parallel sides are often called the bases of trapezoid, with the other sides called the legs. So these two sides are called bases. And the other pair of sides called the legs. The segment that connects the midpoint of the leg is called the median. MN here is a median of the trapezoid. In this case, MN is a median of trapezoid WXYZ. Okay, so have a look at these diagrams, and next let's have a look at the main properties of trapezoids. Okay, I'll give you some time to have a look at these diagrams first. Any questions, just let me know, okay? Alright, if you don't have any questions, let's have a look at an example here. So, suppose we have a trapezoid EFGH here. EF is parallel to GH, and EF is 6. The length of FG is 10. GH is, sorry, FG is 10. So this side is 10, and GH is 12. EH is 8. Can you find the length of the median MN? Okay, again, I'll give you 3 minutes to have a look at that. And if you finish, you can give me your answer in the chat box, okay? Okay, have you finished? Alright, then let's have a look at the solution together. Okay, so let's suppose the extensions of the legs meet at a point x. So this is the original trapezoid. And because EF is shorter than HG, we know that they will meet somewhere here, right? So let's call this point X. So first we can state that the extensions of the legs meet at a point X, and we can easily see that triangle EXF is similar to triangle HXG, right? According to AA similarity, because EF is parallel to HG, right? Therefore, we have XE over XH equals EF over GH, right? And we can substitute XH using XE plus 8. And solving this equation will give us 2xe equals xe plus 8, which means xe is 8, right? And similarly, we know xf over xg is 1 over 2. F is the midpoint of xg. Therefore, we have xf equals fg, which is 10. And also, m is the midpoint of fg, right? Therefore, we have xm equals xf plus fg over 2, which gives us 15. And similarly, we have xn equals 12, right? Since xn over xe equals 12 over 8, which equals 3 over 2, and xm over xf equals 15 over 10, which is 3 over 2, we have triangle XEF is similar to triangle XNM by SAS similarity, right? Therefore, we know that NM over EF equals XN over XE, which gives us 3 over 2, right? Therefore, we know we can find NM is actually 3 over 2 times EF, which is 3 over 2 times 6, which gives us 9, right? So the correct solution is 9. And also we have another conclusion, because angle XNM equals angle XEF. We also have NM is parallel to segment EF, right? Therefore, we have proved two things. First, EF is 6, HG is 12. We have proved that MN is just 1/2 of the sum of the two sides, EF and HG, right? Which is 9. And also we have proved that the median NM is parallel to the two sides, EF and HG. Therefore, this is an important property of the trapezoid. The median of a trapezoid is parallel to the basis of a trapezoid and equal in length to the average of the length of the basis. So in this diagram, suppose the two bases are A and B, median is M, then we know the median MN is parallel to both the two bases, and also we have M equals 1/2 of the sum of A and B. Alright, because we haven't learned how to calculate the area of a trapezoid, right? So let's have a look at this question first. This example will illustrate how we can calculate the area of a trapezoid. So bases PQ and SR have lengths 5 and 9 respectively, and are 8 units apart. What is the area of the trapezoid PQRS? Okay, I'll give you 1 minute to consider this question, and after that we'll have a look at the solution together, okay?
What does it mean they're 8 units apart? Does it mean like the height?
The distance between the two parallel lines is 8. You understand?
Like the shortest distance?
Yes, the shortest distance. Also, the height, yes, you're right, the height of that trapezoid is 8. Alright, let's have a look at the solution here. So, as I told you, we haven't learned how to calculate the area of a trapezoid yet, right? But we do know how to find the area of a triangle. So we can use the formula to find the area of a triangle to help us to find the area of a trapezoid. So we have two bases, 5 and 9, right? And these two sides are 8 units apart, which means we have a height of this trapezoid, which is 8. So we can divide the trapezoid into two triangles by drawing diagonal QS. We can connect Q and S. Then we have two triangles, right? PQS and QSR. Again, we can draw the height of the triangle PQS from point S, which is, the height is 8, right? You know the altitudes QS and SY of the two triangles are both 8, since the parallel lines are 8 units apart. So we have QX equals SY equals 8. Then we can now find the area of the trapezoid by adding the areas of the triangles. So area of PQRS is the sum of the area of triangle PQS plus area of the triangle QRS. which is 1/2 of PQ times SY plus 1/2 of SR times QX, right? And this gives us 8 times half of PQ plus SR. Let's call this point Y and call this point X. Okay, let this height be H, then we have 1/2 of PQ times H plus 1/2 of SR times H, which gives us 1/2 of PQ plus SR then times H, and this number is 56, right? So the area of this trapezoid is 56, and also you can see that the method we can use to calculate area of the trapezoid is here, which is 1/2 of the sum of the two bases times its height, right? Okay, therefore, this is another important property of a trapezoid. Area of a trapezoid equals the height of the trapezoid times the length of the median of the trapezoid, because we know 1/2 of the two bases is the median M. Then the area of WXYZ here of the trapezoid equals 1/2 of sum of A and B, which is M, times its height, H. Did you get it? So please write this down on your notebook, and we could use this to solve some related questions later, okay?
I don't understand why the area, what MH. Oh, okay, I see.
We have just proved this previously, right? M is a median, which means WM equals MZ, XN equals NY, right? If M is a median, then M equals 1/2 of A plus B, right? We have already proved this previously in the previous example, right? Can you follow me?
Yes.
Okay. Therefore, we have this property here. Okay, have you finished? Then we can have a look at another example here. Okay, so first of all, we can draw a diagram to illustrate the situation here. We have W, X, Y, Z, where Wx equals 17, Xy equals 13, YZ equals 21, and XZ equals 20, right? And we need to find the area of WXYZ. So usually, if you want to find the area of a trapezoid, you need the height and two bases. So here we have two bases, and we need the height, right? So we can try to add the height to the diagram in the way that forms useful right triangles here. So let's call this point is H. Then the altitude from X to XY is the most as X. The altitude from X is XH, right? And suppose XH equals H, and also we can let this side be X, and of course ZH would be 21 minus X, right? So first of all, we can have x squared plus h squared. In the right triangle xhy, we have 13 squared, which is 169, right? And consider the other right triangle xzh, we have 21 minus x squared plus h squared equals 20 squared, which is 400, right? So basically, we have two equations and two unknown quantities in which we can solve x and h. We can subtract the first equation from the second, which gives us 21 minus x squared plus h squared minus x squared plus h squared equals 400 minus 169. And this gives us, we can expand everything. This gives us 2, 3, 1, and then cancel x here. Oh, sorry, I lost a plus h here, right? H plus h squared cancel this h squared, so 42x equals 210, right? And this gives us x equals 5. And let's call this number 3. Then we can put number 3 back into equation number 1. And h should equal 12, right? You follow me? So if the height is 12, then we know the area of wxyz, according to the formula, is 1/2 of wx plus zy and times the height h, right? Which is 1/2 of 17 plus 21 times 12, and this is 6 times 38, which is 228, right? Any questions? Alright, if no questions, let's consider another practice. In the trapezoid ABCD, we have AD is parallel to BC, angle B equals angle C, and angle B is less than 90 degrees. Can you prove that AB is actually equal to CD? Okay, first of all, I'll help you to draw the diagram here. So A, B, C, D is the trapezoid. AD is parallel to BC. Angle B here equals angle C. Can you prove AB equals CD? Alright, have you finished? Okay, so once again, we can consider using the right triangles. We can introduce some right triangles to help us, right? So we can draw altitudes from point A and point D. So we draw altitudes of trapezoid A, B, C, D from A and D. So let's call these 2 points X and Y. Then we have AX should equal DY, right? Because both of them are heights or altitudes of the trapezoid. And because AD is parallel to BC, then we have triangle ABX must be congruent to triangle DCY, right? By which theorem should we use here? AAS, right? You see that? Therefore, we have AB equals CD, right? And also notice that we can easily deal with the cases of angle B and angle C being obtuse by noting that if angle B equals angle C, then we have angle A equals 180 degrees minus angle B, which equals 180 degrees minus angle C, which is angle D, right? So no matter angle B and angle C are obtuse or acute, we can always prove that AB equals CD, right? And again, this is another important property of a trapezoid. So two angles of a trapezoid that share one of the bases of the trapezoid as a side are together called base angles of the trapezoid. A trapezoid in which two base angles are equal is called an isosceles trapezoid, which is similar to isosceles triangles, but this time we have a quadrilateral trapezoid. So if the two base angles are equal, then we have an isosceles trapezoid. And isosceles trapezoid has the following important properties. In an isosceles trapezoid, first, the base angles come in two pairs of equal angles as shown at right. A equals D, B equals C. Second, the legs are equal, AB equals CD. And third, the diagonals are also equal, so BD equals AC in this case. You get it? And actually, if any of these items is true for a trapezoid with exactly one pair of parallel sides, then all the others must be true for that trapezoid. Did you get it? And actually, you can try to prove that the reverse statement is also true. So please write this down on your notebook. This is another important property of a trapezoid. Okay, have you finished? Okay, let's summarize what we have learned so far. So we have learned the definition of a quadrilateral, and then we have learned a special type of quadrilateral, which is a trapezoid, and we have talked about 3 important properties of a trapezoid. First, the median is 1/2 of the 2 bases, which is also parallel to the 2 bases, right? For the second property, we have the area of a trapezoid is 1/2 of the sum of the 2 bases times the altitude. And then the third property states that once you have an isosceles trapezoid, then you have the following properties, right? And if any one of these items is true for trapezoid, then you can prove that trapezoid is actually isosceles trapezoid. Then you have the remaining 2 properties, right? Okay, so let's consider one last example for the trapezoid, then we can take a 10 minutes break. So let's do this quick quiz here. Can you find Hj given that Ghij is isosceles trapezoid with Gh equals 8, Hi equals Gh equals 6, and Ij equals 10? Okay, again, if you finish, you can give me your answer in the chat box. GH is a shorter base and IJ is a longer base. Alright, if you finish, let's have a look at the solution together. Again, we have a isosceles trapezoid GHIJ, right? And GH is shorter, which is 8, and IJ is longer, which is 10. And we also know HI is 6, GJ is also 6. You need to find the diagonal HJ. Okay, so in order to find HJ, we can, well, probably find another right triangle to help us, right? We can start by drawing altitudes GY and HX. Okay, then we could consider these two right triangles. These two right triangles must be congruent, right? Why is that? Because this side equals this side, both are the altitudes of the trapezoid, right? This side equals this side, and they also have this angle equals this angle equals this angle, and that means this angle also equals this angle, right? Again, I'm not gonna write all of that. So we know that according to the discussion, then we have triangle GYJ must be congruent to triangle H, oh, this point is X, HXI, right? According to SAS, right? And therefore we know JY must equal XI, right? This side equals this side, right? And also because GY is parallel to HX, so XY is the distance between these two parallel lines, which is also 8, right? And that means JY equals XI, which equals JI minus GH over 2, right? We know IJ or JI equals 10, GH equals 8, divided by 2 gives us 1, right? This side is 1, this side is also 1. And then we consider in right triangle, let's consider right triangle HIX. Well, of course we can find HX here, right? HX is, well, HX square is HI square minus XI square, which is 36 minus 1, which is 35, right? And then let's consider right triangle HXY again as well. So in right triangle HXY, oh sorry, HXJ. Sorry about that. H should be HXJ, right? In this right triangle, we know HJ is the length we want to know, right? And we can use HX and XJ to find it. HX equals, well, HX square equals 35. Actually, we only need HX square, right? And also JX equals YX plus YJ, which gives us 11, right? Therefore, we know HJ square should equal, well, this HJ is a hypotenuse, right? Should equal HX square plus XJ square, which gives us 35 plus 121, which is 156, right? And therefore we know the length of HJ is square root of 156. And that's actually 2 square root 29, right? Oh, sorry, let me check. Calculation might be wrong here. This is not 121. This should be 9, right? Sorry about that. Okay, yx is 8, not 10. So we have 9 here. So that's 35 plus 81, which is 116. And square root of 116 is 2 times square root 29, right? So this is our final solution. Any questions? Alright, if you don't have any questions, let's take a 10 minutes break. And after that, we'll have a look at the definition and properties of parallelogram and Rhombi. Okay, next let's have a look at the concept of parallelograms. A quadrilateral is called a parallelogram if both pairs of opposite sides are parallel. So in this diagram, if we have AB is parallel to CD, AD is parallel to BC, then this quadrilateral can be called a parallelogram. You see the difference between a parallelogram and a trapezoid? In trapezoid, we can only we have if a quadrilateral that has at least one pair of parallel sides, then it's a trapezoid, right? Then if a quadrilateral has both pairs of opposite sides are parallel, then it can be called a parallelogram, right? Okay, then next let's have a look at the property of parallelograms. In parallelogram ABCD as below, the opposite sides are equal, the opposite angles are equal, and the diagonals bisect each other. So can you actually prove this by yourself? Suppose AB is parallel to CD, AD is parallel to BC. First, can you prove that the opposite sides are equal? Okay, let's go to question 1. Second, question B, can you prove the opposite angles are equal? And C, can you prove that the diagonals bisect each other? Okay, I'll give you 2 minutes to think about the question by yourself, and then we can have a look at the solution together, okay? Alright, have we finished? Okay, let's have a look at question A first. Well, if you want to prove the opposite sides are equal, two equal sides, probably you can use some congruent triangles, right? For example, we can connect AC then because we have AB is parallel to CD, then we have angle CAB equals angle ACD, right? Also, because AD is parallel to BC, then we have this angle here equals this angle here, right? And also because they share the same length, AC equals AC, then we have triangle ABC is actually congruent to triangle Okay, so what are the corresponding vertices?
Is it a question for us?
Yes?
CDA.
CDA?
Yeah.
Yes, according to ASA congruency, right? And therefore the corresponding sides are equal, so A have AB equals CD, and also BC equals DA, right? Okay, that proves the first property. If we have a parallelogram ABCD, AB is parallel to CD, AD is parallel to BC, then we have the opposite sides must be equal, right? Okay, next, how do we prove opposite angles are equal? This is also very easy, right? Because we have triangle ABC is congruent to triangle CDA, we have already proved this, therefore we have angle B must equal angle D, right? So we have proved angle B equals angle D. And we also have, well, so let's call this equation number 1 and 2. If you add equation number 1 and 2, then you will have the other pair of equal angles, right? So this means angle CAB plus angle DAC is angle DAB, right? Angle ACD plus angle BCA is angle BCD. Therefore, we have proved the opposite angles are also equal, right? Okay, so how about the next one? The diagonals bisect each other. Okay, then we should connect B and D, right? We need to prove BD and AC bisect each other. How do we prove this? Well, actually, you have already proved that this angle equals this angle, right? This angle equals this angle, right? You also prove this side AB equals this side. Therefore, this triangle, well, let's call this point O. This triangle AOB must be congruent to triangle COD, right? So because of the discussion, I'm not gonna write all of these. Therefore we have triangle AOB must be congruent to triangle COD, right? By ASA congruence. Therefore we have corresponding sides are equal, so AO equals CO, right? And also BO equals DO. Therefore we have diagonals bisect each other. Can you see that? Okay, so this is one important property of the parallelogram ABCD. Okay, please write this down in your notebook. And the question is the reverse statement is also true? Well, actually, the reverse statement is also true. Suppose ABCD is a parallel. Conversely, ABCD is a parallelogram if any one of the following are true, which means if you have whether A or B or C here is true, you can also prove the quadrilateral ABCD is a parallelogram. Can you see that? Can you prove this by yourself? First, if you have AB equals CD and AD equals BC, can you prove ABCD is a parallelogram? Second, suppose you have angle A equals angle C and angle B equals angle D. Can you prove ABCD is a parallelogram? And last, suppose the diagonals AC and BD bisect each other. Can you prove ABCD is actually a parallelogram? Okay, I'll give you 2 minutes to think about this by yourself, and then we can have a look at the solution together, okay? Alright, have you finished? Okay, again we can make use of a pair of congruent triangles, right? We can connect AC. Then if we have AB equals CD and AD equals BC, then because of this we have triangle ABC must be congruent to triangle CDA, right? According to SSS, because they also share the same length AC. Therefore, we have this angle equals that angle here, right? And this angle equals this angle here. Angle CB equals angle DCA. And this gives us AB must be parallel to CD, right? And also angle ACB equals angle CAD, and this gives us AD is parallel to BC. Therefore, we have proved two pairs of parallel lines, and according to the definition of parallelogram, If both pairs of opposite sides are parallel, then we can call this quadrilateral a parallelogram, right? So we can actually prove the first one. You see that? How about the second one? If we have A equals C, if you have angle A equals angle C and B equals D, well, actually the method should be the same, right? We can make use of a pair of congruent triangles. A equals C, and B equals D. How do you prove ABCD is a parallelogram? Okay, first we can connect A and C as well, right? So, any ideas? Well, sorry, actually, you don't have to, because, well, if angle A equals angle C, angle B equals angle D, then we know angle A plus angle B must equal angle C plus angle D, right? Which is 360 degrees over 2, which is 180 degrees, right? So if angle A equals angle B equals 180 degrees, because angle A and angle B are the same side interior angles, so we can prove AD is actually parallel to BC, right? And if we can also have angle A plus angle D equals angle C plus angle B, which is also 360 degrees over 2, which is 180 degrees. This means AB is parallel to CD, right? So we can prove this is actually a parallelogram. You see that? Okay, and for the third one, if the diagonals AC and BD bisect each other, so let's draw the bisects first, which means this side equals this side equals this side. Can you prove AB is parallel to DC? Of course, this is also very easy, right? We can make use of these two triangles. The triangle ABO is congruent to triangle COD, right? Because this side equals this side equals this side, and they have a pair of vertical angles, right? Therefore, you can prove this angle equals this angle here. That means this line is AB is parallel to CD, right? And using the same method, you can also prove that triangle AOD is congruent to triangle BOC, which means this angle equals this angle here, which proves this side AD is parallel to side BC, right? Therefore, again, you have two pairs of opposite sides, and then the quadrilateral ABCD must be a parallelogram according to its definition, right? So this property is actually reversible. So let's make a summary here. In a parallelogram ABCD, the opposite sides are equal, the opposite angles are equal, and the diagonals bisect each other. And conversely, ABCD is a parallelogram is if any one of the following are true. Okay, be careful with the keyword here. Any one of the following. First, AB equals CD and AD equals BC, or angle A equals angle C and angle B equals angle D, or diagonals AC and BD bisect each other. Any questions? All right, then if you don't have any questions, let's have a look at Another example. So here in this diagram, side EU and NT of parallelogram ENTU are 5 units apart as shown. EU is given as 12, EN is 8. A, can you find the area of parallelogram ENTU? B, how far apart are sides EN and TU? And be careful that we haven't learned any formulas to calculate the area of a parallelogram, right? So we can only make use of what we have learned so far. We learned how to calculate the area of a triangle, right? So probably we can connect ET or NU. Suppose we connect ET, then we know that the area of the parallelogram ENTU can be calculated by adding up the triangle area of triangle EUT and the area of the triangle ENT, right? And we know that the area of triangle EUT is 1/2 of the base, which is EU, times the height, which is the distance between EU and NT, right? Which is h. Of course, here h equals 5. Can you see that? And ENT is, area of ENT is 1/2 of NT, the base, times the height h, right? So that gives us 1/2 of h, then times either EU EU plus NT, right? No, actually EU plus NT, because EU equals NT, right? This is a parallelogram, so opposite side should be equal. So therefore we have 1/2 of h times 2NT, which gives us actually NT times h. You see that? Which is 12 times 5, which is 60, right? And if you know the area of the parallelogram ENTU, then it's very easy to find the distance between EN and TU. So as you can see here, the area of the parallelogram can be given by the base times its height, right? Therefore, if you are using if you are using UT as EN as the base, then you should multiply this by the corresponding height. So let's call the height here as h1. This is a distance between EN and TU, right? And that gives us 60. Therefore, we know the distance you are looking for, which is h1, equals 60 over EN, which is 8. And this gives us 15 over 2, which is 7.5. Did you get it? Any questions here? So this actually gives us a method to calculate the area of a parallelogram, which is its base times its height. Suppose we have parallelogram as shown on the right, ABCD. Then the area of ABCD can be calculated using AB times XY or BC times PQ. XY and PQ are the corresponding heights. Okay, and this is another important property of a parallelogram. Please write it down on your notebook. Okay. Have we finished? Alright, then let's have a look at another type of quadrilateral, which is called rhombi. Actually, rhombi is a plural form of the word rhombus. A quadrilateral is a rhombus if all of its sides are equal. So suppose we have a diagram here. If AB equals BC equals CD equals DA, then this quadrilateral is called a rhombus. Also note that if AD equals BC and AB equals CD, we can prove this is actually a parallelogram, right? So every rhombus is also a parallelogram. Therefore, all that is true about parallelograms is also true about rhombi. Did you get it? Okay, then let's have a look at a special property of a rhombus according to this introductory example here. Suppose ABCD is a rhombus such that its diagonals AC and BD have lengths AC equals 30 and BD equals 16. Can you find AB and AB? Can you find length of AB and area of ABCD? Alright, have we finished? Any ideas? Okay, first let's draw a rhombus first. So a rhombus is also a parallelogram, right? And actually the four sides are all equal. So AB equals BC equals CD equals AD, right? And we know the length of the two diagonals, so let's connect the opposite vertices. Let's call this point X here. Okay, all four sides of rhombus ABCD are equal, and that diagonals bisect each other, right? Because the rhombus is also parallelogram. For a parallelogram, the diagonals bisect each other. Therefore, we have bx equals xd, right? ax equals xc. Can you see that? Therefore, because of this, I'm not going to write all of this. But because of the discussion here, we have triangle ABX must be congruent to triangle CBX, which is also congruent to triangle CDX and congruent to triangle ADX, right? All of the four little triangles are congruent. Also, this angle equals this angle equals this angle equals this angle, which is a quarter of 160 degrees, right? Therefore, we have BX is also perpendicular to AC, right? And therefore, we know the area of ABX can be given as 1/2 of BX and AX, right? Because BX is perpendicular to AX. And that is 1/2 of BX. BX is 1/2 of BD, right? Which is 8 times AX is 1/2 of AC, which is 15. So that means the area of ABX is 60, right? And therefore we have the area of ABCD is 4 times the area of the little triangle ABX, which is 4 by 60, which gives us 240, right? And then AB is square root of bx squared plus ax squared, right? Which is square root of bx is 1/2 of bd, which is 8. Ax is 15. So that is square root of 64 plus 225, which gives us square root of 289, which is 17, right? Did you get it? And also note that the area of ABCD is actually can be represented by twice of AX times BX, right? Because this is actually 2 of AC over 2 times BD over 2, which is 1/2 of AC times BD, right? So this is another important property of the special parallelogram rhombus. So let's make a summary here. The diagonals of a rhombus are perpendicular. The area of a rhombus is half the product of its diagonals. Of course, it's also base times height, since the rhombus is also a parallelogram. You see that? So suppose you have a rhombus here. The area of rhombus ABCD is given by 1/2 of AC times BD. Okay, please write this down in your notebook. And that concludes our lesson today. Okay. Alright, so I'll give you the homework to Google Classroom. Remember to complete them before the deadline, preferably one day before the deadline, so I have time to mark them. Okay. Alright, so class dismissed for today.